When you ask people about project portfolio management, they tend to have differing opinions about how it should be done and how it is done. Some see it as a basic capital budgeting problem and focus on payback periods and profitability indices. Others see it as a strategy problem, and they focus on the complex interdependencies among the various projects. Others merely see it as a political issue where the high-level stakeholders lobby to have their favorite projects funded and ignore everything else. Unfortunately, when you try to reconcile all three of these factors, the overall decision process can be very time-consuming, and the final result is often far from optimal. Fortunately, there's a better way. In order to help our clients make their project portfolio management processes faster and more effective, the InnovaNet team has developed an Excel-based model that can be used to solve general PPM problems. Consider this simple example. Here we have a portfolio of 10 potential projects. Each project has certain costs and benefits and resource requirements. There are also precedence constraints among projects. For example, projects A and B have to be executed before project C can be executed. There are also mutual exclusivity constraints. For example, you can execute either project C or project D, or neither, but you can't execute both. Taking all that into account, the question is then which projects you should execute and in which order without exceeding any limits on financial or human resources. Consider this example. Suppose a manufacturing company has a list of candidate projects, and they'd like to know which subset of projects to do and in which order, such that the overall net present value is maximized and the overall production capacity is maximized. In choosing the subset of projects that offer the best results, the company must also respect all the constraints, which include precedence constraints, budget constraints, resource constraints, and mutual exclusivity constraints, as well as political constraints requiring that certain projects be executed and others not be executed. If the portfolio contains only a handful of projects, then the problem can easily be solved by hand. However, when the portfolio contains dozens of projects and constraints, the problem gets very complicated very quickly, and it can be difficult to find even a decent solution by hand, let alone an optimal solution. Rather than decision makers spending days debating a difficult PPM problem, our model can solve it in minutes. Here is a high-level view of what the model looks like from the user's perspective. The model resides in Microsoft Excel, so the input data and output data is in Excel. The primary advantage is that users get the familiarity of the Excel interface, and cells can be linked to other spreadsheets. As far as inputs, the user has to specify some global parameters, including discount rate, inflation rate, and annual budgets. The model also allows the user to specify relative priorities for the different objectives. In this example, the only budgets that need to be respected are the capital budget and the human resource budget, but the model could be configured to take into account several budget and resource constraints. Then the user inputs various information about each project, including duration and expected cash flows over time. The model also allows the user to specify a forcing parameter for each project, which will either force that project to be executed, along with its predecessors, or force it to not be executed, along with its successors. This allows for management preferences based on other objectives to essentially override the model. The user also has to specify the precedence and mutual exclusivity constraints. Then, to run the algorithm, the user merely initializes the start dates and clicks Run, and the algorithm varies the start dates for all the projects in a systematic way until it finds the best solution that respects all the constraints. After the algorithm has finished running, the output is simple. The model tells you which projects to execute and when to start each one. It also calculates various other metrics to show the results that will be obtained by executing that particular set of projects. Looking at the actual model, here's where the user would enter the global parameters. These include inflation rate, discount rate, and the relative priorities that the user would like to assign to the two different objectives. Here's where the user would input the data for the individual projects. So we see that each row corresponds to a different project, And for each project, we specify the value for the forcing parameter, the duration, and the production capacity before and after the completion of the project. Then the user would need to enter the capital costs for the projects. Then the user would input the incremental revenue for each project. The next step is for the user to enter the data specifying how much human resources we would expect each project to consume in each year. In this example, we are looking at design engineer resources. Here the user enters the precedence constraints by specifying each predecessor-successor pair. For each of the constraints, you can specify whether it's a finish-start, start-finish, start-start, or finish-finish. The last data that the user needs to input is to specify which pairs of projects are mutually exclusive. Here we see our decision variables. Here the user simply clicks a button to initialize the values for the start year and the upper and lower bounds. Then, when the user sets the algorithm in motion, the algorithm will vary the values of the start years in order to maximize the value of the objective function. Note that if the start year is equal to 0, that means that the project will not be executed. Now, supposing that we've already entered all the input data in the model, let's see how it runs. After we've entered all the necessary input data, the next thing we need to do is to initialize the start year and the bounds. This macro just initializes the start year values to 0 and adjusts the values for the upper and lower bounds to take into account the projects that have been forced into the schedule or forced out of the schedule. This helps the algorithm arrive at a good solution faster. Then, all we need to do is to open the Excel Solver interface and run the algorithm. The cells containing the objective function, the decision variables, and the constraints have already been specified, so all we need to do is click Run. Here the algorithm sets up the problem, and we can see that it took a total of less than 4 seconds to set up the problem. We can also see it has already found a feasible solution. Now it will continue to run, and the objective function value will continue to increase until either a stopping condition is satisfied or the user stops the algorithm manually. When the algorithm is running, we can also see how many constraints are being violated. So here we can see that the algorithm is not only looking at feasible solutions. In fact, because the feasible region in this model is so complex, the algorithm does not know in advance which of the solutions will be feasible. However, when the algorithm is stopped, the best feasible solution found so far will be displayed in the blue cells. We can also see what's happening to the bottom line metrics while the algorithm is running. We can see that sometimes Z is getting better and sometimes worse, but the algorithm always keeps track of the best solution found so far. Now we'll go ahead and stop the algorithm manually. Now we can generate a basic project plan by clicking on the appropriate macro button. And then everything gets copied over to another sheet and sorted and filtered so that we only see the projects that actually made it into the schedule. If you'd like to get a copy of the model that's configured to solve your particular PPM problem, please contact InnovaNet.